Hello, my name is Igor Kadota. I'm a postdoctoral research scientist at Columbia University. And today I'm going to talk about spectrum sharing via consumption models. First, I'd like to thank Ray for the invitation. I met many of you online in Zoom meetings, but finally I met you now in person. So as you can see, the big team in this project with researchers from Columbia, Syracuse, and Rutgers. So Sad, Carlos, me, Dragoslav, Trevor, Asha, Azan, Gil, Ivan, and Ray are some of the researchers in this project. So I'm going to get started. If you have questions, also feel free to interrupt me. So the overarching goal of the project is this, right? To design and evaluate dynamic spectrum access techniques that leverage collaborative methods for our systems to declare their intentions to use, as well as their needs in terms of interference protection, right? So there has been a lot of research on DSA algorithms, but mostly focusing on theory and also focusing not on collaborative methods, right? Usually you have radio, they're sensing the environment, they kind of learn what's going on in the environment, and then they adapt to that, right? But in this product, we are trying to emphasize implementation or evaluation and also collaborative methods. There are two distinctions that matter. So this is the outline of the presentation. I'm going to start by briefly introducing this concept or this new standard that introduces the spectrum consumption models. Then I'm going to discuss some DSA experimentation that we did in the Cosmos testbed. In fact, this was done here in the orbit grid. Then I'm going to discuss sequential versus distributed DSA algorithms. Then I'm going to follow up with ongoing and future work. Okay, so SCM, spectrum consumption model. So the motivation here is that we want to create like a language for RF systems to communicate their intentions of using the spectrum and also what they need in terms of protection, right? And the IEEE has come up with this standard that offers a language, right? A mechanism for RF systems to declare their intentions of using the spectrum and also what they need in terms of protection. But this standard also creates a mechanism for the RF systems to determine compatibility, so to run compatibility tests between different RF systems, between different radios, right? So SCMs, they use a set of 11 constructs. I'm going to go over a few of them in the next slide to describe the spectral, spatial, and temporal characteristics of the spectrum use and needs of those RF systems. So some constructs here. So reference power and spectrum mask, they basically, so this is an example of a spectrum mask, right? Together, they capture the spectrum content of the transmitter, right? What the transmitter is going to transmit. And here, the reference power and the underlay mask, which is here, they capture the amount of protection that you want. So if you're a receiver, you don't want to receive more power than this on this particular frequency, right? So this is how to characterize what you're going to transmit, what you need in terms of protection. And you also have a few other constructs, such as power maps, which capture antenna gains and directivity, propagation maps that capture the environment, the path model, the path loss model, scheduling in terms of defining the. So if you're creating a SCM with those constructs, you can determine a time in which that SCM is going to be valid, right? If you plan to transmit only from only today, then you can just define that in your schedule and have that built in. And most of those, just a note that most of those constructs, they have a probability data elements inside, so you can also kind of characterize uncertainty and variable characteristics of your RF system. And Professor Carlos Bastistas from Syracuse University is a member of this working group creating this SCMs. So if you have questions, specific questions about some of the constructs or how to do compatibility tests, he's a great point of contact. And on ongoing work, so we have a lot of campaigns in Cosmos at Columbia, and here there are a lot of people in this field, for instance, that are here in the room. And we do channel measurements at millimeter wave frequencies. And what we want to do is we want to get those measurements and create a pipeline that basically uses Python code to go over all the measurements and then create SCMs based on those millimeter wave measurements and use those in simulation. Right? So that's the basic idea, to create SCMs based on real measurement output. Now, I briefly introduce SCMs. I'm going to talk a little bit about our experimentation, and probably you know the Dragoslav and Prasad. This is work that was published in WinTech 21st, spectrum consumption model-based framework for DSA experimentation in Cosmos. So basically, basically what we have here is this infrastructure, right? So this infrastructure is based on the DARPA Collaborative Intelligence Radio Network Interactive Language, which I'm going to just call SIL. And we implemented this in the Orbit grid, right? And one great thing about Cosmos and Orbit is that this is freely available, right? So if you want to use it, there are images there that you can just load and then use this kind of a system. So we created this infrastructure that has wireless domain controllers. I'm going to, in the next slide, I'm going to talk about what is this, right? But we have also a regional controller here centralizing our collaboration. And wireless domains, they communicate using this SIL protocol, the SIL language, and one thing that was not there in the DARPA Spectrum Challenge are those exchanges of SCM. So we implemented this exchange of SCMs as well, so that domain controllers can communicate among themselves what are the needs and uses of the RF spectrum that their radios are going to need and do, right? So that's the infrastructure that we built. And the WD controllers, they basically manage the SCMs associated with the radios that are associated with them, right? So they have a number of radio pairs. Those radio pairs will create SCMs, and the WD controller is going to manage those SCMs. And the regional controller is going to keep track of topology, right? So if these radios are going to interfere with those radios, basically the regional controller is going to know this, and it's going to notify WD controller such that they can exchange SCMs. You're going to see this in the next slide, such that they don't interfere. So that's the basic infrastructure that we built. And now I'm going to run over one example, right? Suppose that those two radios, they appear and now they are associated with this particular WD controller. What happens? So the WD controller is going to notify the regional controller. The regional controller is going to inform this WD controller. The regional controller is going to inform the WD about what are the peers, what are the neighbors, right? And now the WD is going to directly communicate with neighbors and ask for SCM. And now those SCMs, they're going to those SCM from other neighboring WDs, they're going to inform this WD about what are the transmissions going on and what are the protections that the neighbors need, right? So now that the new WD controller, the WD controller with new radios knows about the environment, it will run compatibility tests and figure out what it can do, what frequencies it can use, what power it can use, at what time. That's the basic idea of the infrastructure. So we implemented all of this in Cosmos. And of course, if the WD cannot find resources, then if you can't find that, then the link is established. Otherwise, this link is dropped and can never join the network, right? Because there are not enough resources. Yeah, one interesting thing that we're going to see in measurements later is this. One interesting question is, how large should it be your neighborhood, right? If your regional controller is overestimating the size of your neighborhood, then you're going to need a lot of SCM exchanges, and the compatibility test may take longer than needed. In contrast, if you're underestimating your neighborhood, then you're not getting all SCMs, all information that you need, and you may end up with harmful interference. And that's something that we're going to see soon. But next, we're going to go to a video of the Cosmos implementation. This is basically the Orbit grid that you all know. Basically, this is a schematic of the links that we use, right? So this is one transmitter, one receiver, transmitter, receiver, transmitter, receiver. All three links will interfere if you try to use them in the same frequency. So some of the parameters, we use a central frequency of 2 gigahertz, much lower than someone. Band is 1 megahertz, but this was basically a proof of concept that we implemented the infrastructure and it was working, right? So here you can see that we have already 2 links established. Now the third link is trying to come and join the network. There are SCM exchanges. They run the compatibility test, figure out that we cannot transmit here, cannot transmit there, so we're going to choose this one. And here we have 2 X310s transmit and 1 V210 starts to transmit, and you're going to see that the shape of the signal is a little bit different, and there's some out-of-band interference, and this has to be taken into account when you're doing compatibility tests, and it is. Okay, so that's the infrastructure that we built. That's something that we're going to leverage also in future experiments. And again, available for everybody that wants to use. In terms of DSA algorithm. And here we're going to, so there's a mastermind behind all of this, right? So he's the one that made all of the work and implemented a lot of it. So in sequential DSA algorithm, wireless nodes, they appear one at a time, right? And that's something that also happens in practice. So A new pair appears, SCMs are collected from the neighbor, you run compatibility tests, you make sure that there's no interference, and then the new link is set or dropped, right? Sequential DSA. On the other hand, what happens if you have a distributed case in which multiple nodes appear, right? Then what would happen there? One challenge is if you have multiple pairs appearing, the new pairs of radius, they don't have information about what they're going to do. So they don't have SCMs. And so that's a challenge. We have to address that. But there's one opportunity, which is if you have this kind of scenario, it might be the case that you can run compatibility tests in parallel. So you can take less time to converge to the final state of your network. And we're going to see those two things in some simulation. Okay, so in terms of distributed DSA algorithms, right? So if two pairs appears, one pair of radius appear here in this WD and the other one there, right? They're in different neighborhoods. So basically what can happen is they don't need to know each other's SCM. They can both create new SCMs and they can both start transmitting. They can both do their own thing and start transmitting faster, right? However, if you have two new pairs of radios in the same neighborhood, then there needs to be some type of conflict resolution. And that's basically one thing that we develop a protocol for conflict resolution when you have this kind of distributed algorithm. Fortunately, the protocol is kind of a little bit complicated, so I'm not going to go over the details, but we have some simulations to show this. The improvement in terms of time that you can get when you compare sequential and distributed. So this is the simulation setting. We have an area of half square mile, which I'm from Brazil, so I use kilometers, so 1.2 square kilometers. Transmitters are placed at random. Receivers are placed uniformly in a circle or donuts around the transmitter, uniformly between 10 meters and 100 meters, right? And then the SCMs that we're using, so for instance, if you have a simulation and you want to simulate some of those SCM exchanges, you can come up with synthetic ones. But what we did was we used SCMs from the measurements in Cosmos to make it more realistic. But what you could do also is to use, for instance, millimeter wave SCMs and kind of have some directionality playing a role here. And that's something that we're currently working on. But the SCMs that we use here, they were from Cosmos, and they have those features. The initial center frequency that radio start to try transmitting would be 2 gigahertz, and this frequency can be increased in steps of 1 megahertz. So you can change the frequency in which you're transmitting. That's one parameter that you can change. The other one is power, right? So your initial power is 1.5 dBm, but you can reduce that up to a limit, right? Because you don't want to have too much of a lower capacity. So two variables that you can change when you're trying to start communicating a network: frequency and power. You cannot, in this particular simulation, you cannot change time. We are assuming that we have continuous transmission, right? If a link is established, it will use that particular resource for a long period. And neighborhoods, and that's something that we're going to have in the simulations, they're defined by these radius P, which can be anything that you want, but in our simulations, we use either 100 meters, 200 meters, 500 meters, or infinity. Infinity meaning you have a click, right? Everybody's neighbor, so you're considering everybody when you're trying to start to transmit. Okay, so we measured global compatibility error, because remember I was talking about neighborhood, right? So if your neighborhood is too small, you might not consider some transmitters, and you might get some error in terms of interference. That's what this cap is. That's the first column here. The second column is just system capacity, which is the sum of the capacities of the links. Channel usage, that's something that you usually want to limit when you're doing DSA, right? You want to not use too much bandwidth, right? You want to keep the radius as packed as possible. So this is the number of channels used by that particular network. And also the computational time. So for instance, in the sequential, you have one link appearing after the other, right? So how much time does it take to convert and set up all the 100 links in that case? And on the other hand, on the distributed, you have all 100 links appearing. But then how much time does it take to deconflict all of them and set up all the 100 links, right? So here we have 3 sequential algorithms. The difference here is that this sequential algorithm can only change frequency, so it cannot change power. So it has to use the maximum power. So that's going to have, for sure, the highest capacity or the highest throughput. And this one, the first one, can change power to the limit that you want. It can change power as it wishes. So we're going to have lower throughput, what we expect to have a more packed network, right, with less frequency use. And you have 3 distributed algorithms with different neighborhoods, so 100, 200, and 500 meters neighborhood. those are the DSA algorithms that we're simulating. And a lot of numbers, I'm going to walk you through the more important ones, and probably you cannot even see what they are. So I'm going to walk you over. Distributed with a very small neighborhood, you get a lot of compatibility errors, right? Of course, you're not considering everything, so you get errors. We don't want that, so that's something that we don't consider even in terms of other metrics, right? The important thing is that it has errors, so we should consider a larger neighborhood. But when we compare sequential with distributed with a larger neighborhood, then we can see that they are basically the same in terms of throughput and the same in terms of packing, how much they can pack the network in terms of frequency, right? So for 100 links in the network, they use around 13 frequencies, and the throughput is around 360. However, the main advantage here is that the lower the neighborhood of your distributed algorithm, the shorter the time that it takes for each convert. So here it just takes 17 seconds. On the other hand, for the sequential, it takes 325 seconds to convert. And that's basically counting only compatibility test time. So distributed with as low as possible neighborhood is the best that you can do, without errors, of course. So here is computation time versus number of transmit receive pairs in the network. As you can see here, the smaller neighborhood of 100 with error gives you the best, but of course it has error, so we don't want to do that. The next best one would be distributed with a neighborhood of 200 meters, which gives you this 17.12 seconds of conversion time. Okay, another interesting comparison is what is that power adjustment gives you, right? That's something that is kind of unique to SCMs. If you're doing just sensing, you cannot really fine tune your power in order to not interfere with others, right? You kind of like, if you're doing just sensing, sense that your network, your frequency is being used, you cannot just use it, right? But with SCMs, you have more knowledge. So you can fine tune your power in order to pack more links in the lower band. So when you compare frequency only, so you cannot change your power, you get a higher throughput, of course, but you have to pack your 100 links in 14 frequencies. But when you can use your power adjustment, you have a slightly less throughput, but you can pack your 100 links in just 12 frequencies. So that's the trade-off. And here you can see the red one would be without adjustment of power, the yellow one, the distribution of the links over the frequency, number of channels used versus number of links. And here you can see that you use much lower number of links if you can use power. And in terms of future work, the main results that I just showed were implementing a simple DSA algorithm based on DARPA-C protocol in orbit, simulating the large-scale DSA algorithms using sub-6 gigahertz SCMs, and creating SCMs based on millimeter wave measurement. Right? Those are things that we are currently doing. In terms of future work, we would like to develop enhanced, centralized, and distributed DSA algorithms for sub-6 gigahertz, but also for millimeter wave networks. So we would like to include algorithms that account for time-varying transmissions instead of continuous transmission, antenna directionality, and wireless node mobility. But the mobility is something that's a little bit further in the horizon. But those two ones we are trying to tackle right away. And also develop traditional. So we were doing collaborative algorithms and focusing on implementation, right? But there's a lot of algorithms out there which are non-collaborative. And we would like to leverage some of that knowledge out there in the literature. In fact, we are implementing one of these, which is based on reinforcement learning. I recently got like a GNU Radio screenshot from one of our collaborators, and he's trying to implement reinforcement learning algorithms in GNU Radio. And I don't know the results yet, but I'm excited to see what we will get. And the idea would be to compare this with SCM-based algorithms. And finally, evaluate and compare those algorithms in Cosmos, so in practice, and also using simulation. That's it. Comments.
I could just mention that NSF has a program called NRG, which is a spectrum management and spectrum measurements activity that we just started this week under the umbrella of something called Spectrum innovation as the main program. And within that is this NRDP, which also looks at experimental activities in 2 or 3 sites which have been designated. So he is from Colombia, where we have one of the sites at which these kind of experiments can be done. So they can do a lot more with real world data than has been possible in spectrum.
And I just wanted to say that AT&T is proud to have submitted a letter of collaboration and supporting this work. Spectrum's huge, obviously. There's still a lot of hesitation on the part of global tier 1 operators to share licensed spectrum, but that's something we'll have to chip away at. Thank you.
So this topic never goes away. Spectrum has been discussed at IAB meeting 20 years ago. Things change very slowly, but I think the SCM standard from IEEE that is a big break, and it might help to move things to a more quantitative approach. Okay, anything for Igor? Okay, thank you.